Assalamu alaikum everyone. I, Hina, welcome you all to another tutorial of electrical measurements. So far we have completed the 3 topics of this unit and now we are only left with 2 topics. Today our topic will be various forces in electromechanical indicating instruments. We are all aware that any indicating instrument that we see in our labs, for example a meter, voltmeter, it has a pointer that's moving over a calibrated scale, and by seeing where the pointer is on the calibrated scale we are able to take the readings. So the point is where the pointer is indicating on the calibrated scale. By knowing that, we are able to take the readings. So what are we going to learn is that how the pointer will move from its initial position and stop at exactly the same value that we are going to measure. Okay, for example, if we are measuring a current of 5 amperes, our aim should be that the pointer should exactly stop at the 5 amperes, not at 5.1 or 4.9. We will learn this, how the ammeter will be able to take a reading of exactly 5 amperes. So any indicating instrument is able to take the reading with the help of 3 forces, that is deflecting force, controlling force and damping force. We can also use the term torque in place of force, so we can say deflecting torque, controlling torque and damping torque. Now starting with the deflecting torque. Deflecting torque or deflecting force, it's also known as the operating force. Okay, now we all know that when we are not taking any reading on any instrument, the instrument will be at 0 position. Now what deflecting torque or deflecting force does, its aim is to move the pointer from the 0 position. Okay, and any system that produces the deflecting force is known as deflecting system or moving system. So a deflecting system or moving system can be defined as any system which moves the pointer from the 0 position. And this deflecting force can be produced by any of the effects that we read in the last class, that is magnetic effect, thermal effect, electrostatic effect, induction effect or Hall effect. Okay, so what the deflecting system does, it actually converts any electrical current or potential into deflecting force. That's also mechanical force, but because it moves the pointer. Okay, this deflecting system, so we can say that this deflecting system acts as a prime mover that is responsible for the deflection of pointer. Now coming to the controlling force or controlling torque. See, we all know that if only deflecting torque was acting in the system, the pointer would continue to move indefinitely till it reaches the maximum value. But that's not what we need. For example, if we want to measure a current of 5 amperes and we only provide deflecting torque, then the pointer will move from 0 position, but it will not at all stop at 5 amperes. It will go beyond 5 amperes. What the function of controlling force is? The function of controlling force is that it will stop the pointer exactly at 5 amperes. Okay, so this force produces a deflection that is directly proportional to the magnitude of the measurement, that is current in this case. And the system that will produce the controlling force will be known as the controlling system. So we can say that the controlling system will perform 2 functions. First, it will stop the pointer at the final steady state position. It will not let the pointer go beyond that position. Controlling system will be able to do so by producing a force that will be equal and opposite to the deflecting force at the final steady state position. And second function that the controlling system will perform is that it will bring the moving system back to 0 when the force causing the deflection is removed. That means if you are not measuring any quantity, the pointer will automatically point at 0 position. Okay, now we all know that what controlling system is, what's its function. Now in any electromechanical indicating instrument, there are two types of controlling systems that can be employed. First is gravity control and another is spring control. Okay, so first we will understand what gravity control is. In gravity control, what actually happens is that a small weight is placed on an arm that's attached to the moving system, and the position of this weight is adjustable. So in gravity control, we will have two weights. First, adjustable weight and another control weight that will be attached to the spindle. Control weight will provide the controlling torque, and controlling torque will be provided due to gravity, hence the name gravity control, while the other weight is for balancing the weight of the pointer. Now, if we consider the zero position, the weight will be acting vertically downwards and it will be W. It will be simply W. But when the pointer is deflected through an angle, the controlling weight will have a position, that is W sine theta will act now, because its position is displayed. It's now not vertical. So if we will see the controlling torque, we all know torque is represented by formula force into force arm. So the force acting here is W sine theta, the component W sine theta, and the distance is L. So controlling torque will be represented by the formula WL sine theta, where W and L both are constants, so WL will be constant. Hence we can say that controlling torque will directly be proportional to the sine of the deflecting angle. Therefore, controlling torque can be varied by simply adjusting the position of control weight upon the arm which carries it. Now coming to the disadvantages and advantages of gravity control. First, disadvantages. The main disadvantage of gravity control is that it can only be used vertically. That is, it can be used in only vertically mounted instruments. The second disadvantage is that in case of gravity control, the instrument must be perfectly leveled. Now, advantages of gravity control are that it's cheap and the control is independent of temperature variations and it does not deteriorate with time. Another way of providing controlling torque is by using the spring control technique. In spring control technique, the controlling torque is provided by the hairspring attached to the moving system. But the spring that is used in spring control should follow some characteristics, and they are that they should be non-magnetic in nature, they should not get mechanical fatigue, and in places where springs are used to lead current into moving system, they should have a small resistance. That means that it's dependent on resistance, and we all know that resistance is defined in the formula R is equal to rho L by A. So where springs are used to lead current into the moving system, they should have a small resistance. The cross-sectional area must be sufficient to carry the current without temperature rise affecting their constant. They should also have a low resistance temperature coefficient. That means it depends on the temperature as well. Most suitable material that is used in spring control is phosphor bronze. It's almost used everywhere except in instruments of low resistance like millivoltmeters. For millivoltmeters, we use special bronze alloys that have low resistance. Now, what happens in the spring control is that you can see in the figure that the inner end of the spring is attached to the spindle and the outer end carries a spigot which engages in a circular disc surrounding the jewel screw. This disc carries an arm which is slotted and flayed out at the end. The purpose of slotted extension arm is to allow the spring to be coiled or uncoiled slightly so that the pointer may be set at 0. The slotted arm is actuated by a set screw mounted at the front of the instrument, and therefore the 0 setting of the instrument can be done without removing the cover. The formula for controlling torque using the spring control is EBT cube theta upon 12L, where E, B, T, 12 and L all are constants. So we can write the controlling torque is directly proportional to theta. And remember, in gravity control it was directly proportional to sine of theta. Here it is directly proportional to theta. Okay. Now we will see the dependence of controlling torque on theta and sine theta, and what will be the effect of this dependence on the shape of scale. By the shape of scale here we mean whether the scale will be uniform or non-uniform. Okay. First, let us consider the case for spring control. As we already derived, for spring control, the controlling torque is directly proportional to deflection, that is theta, and the deflecting torque in any case is directly proportional to current. Okay. At equilibrium position, the controlling torque will be equal to the deflecting torque. So we will equate the above two equations, and what we will ultimately get is that theta will be equal to K2 times I, where K2 is the constant of proportionality. So we can say that in case of spring control, theta is directly proportional to current. Means whatever will be the increase or decrease in current, it will have the same effect upon the deflection. If current will increase, deflection will also increase. If current will decrease, deflection will also increase. So throughout the whole range of the measurement, theta will be directly proportional to current, and therefore we can say that for spring control the scale will be uniform. Okay. Now coming to the gravity control. In gravity control, the controlling torque was directly proportional to the sine of deflecting angle, that is Tc is equal to kg times sine of theta, and deflecting torque is as always proportional to current. So at equilibrium, controlling torque will be equal to the deflecting torque. On solving, we will get that deflection is equal to sine inverse of K2 dash I. That means here deflection is not directly dependent upon current. Here we have a factor of sine inverse. Now if we substitute theta equal to 90 degree for maximum current and put it in the equation theta is equal to sine inverse of K2 dash I, we will get K2 dash equals 1 upon I max. Now if we will try to find the value of theta for half the value of maximum current, upon solving, as you can see in the slide, we get theta equals 30 degree. But if we compare this with the gravity control, there for half the value of maximum current, theta was 45 degree, and there the scale was uniform. Here theta is 30 degree. That means deflection is different. So here we will not have uniform scale. Therefore, for gravity control, the scale is non-uniform. Okay. Now this slide will help you to easily differentiate between the spring control and gravity control. The various points are here, like cost. Spring control is costly, while as gravity control is cheaper. The most important difference, that is the difference in their scales. Spring control has uniform scale and gravity control will have a non-uniform scale. And another difference is based on the temperature. Temperature will cause some errors in the spring control, while gravity control is independent of temperature. And the last point, that is due to spring tension, the spring control deteriorates with time, while as this is not the case with the gravity control. Now coming to the last force, that is damping force. When the deflecting torque is applied, the pointer moves, and when the controlling torque is also applied, the pointer stops where we have to take the reading. But this damping force is necessary. Why? Because the pointer has some inertia, and for example, if we have to take a reading at exactly 5, the pointer will not stop immediately at 5. It will oscillate. It will move from 4.8, then go to 5, then 5.3. It will keep on oscillating. This oscillation happens because of inertia. So the damping force is required to overcome this inertia such that the pointer will stop exactly at 5. Okay? We people can easily relate this with the case of simple pendulum where for example 0 is the final state of the pendulum, but the pendulum will keep on oscillating between B, O, A, then again to O, then B. Then with time the amplitude of oscillations will decrease and the pendulum will ultimately rest at O. Same happens here. For example, the final reading is at O, but due to inertia the pendulum will move to B, but there the controlling torque will be greater than the deflecting torque, so it will try to come back to O, but due to inertia it will again overshoot that point. It will reach at A, but at A the deflecting torque will be more than the controlling torque, so it will again try to move to O. This process will repeat. But if friction will be there will come a time when the amplitude will go on decreasing and decreasing, and ultimately the pointer will rest at O. So what the point is, we have to provide some sort of friction such that the pointer will rest at O. So this extra force in the form of friction or whatever we can provide, this extra force that we provide to damp those oscillations is known as the damping force. And this damping force is necessary so that the moving system comes to equilibrium position rapidly and smoothly without any oscillations. So now we are all aware that there are 3 forces: deflecting force, controlling force and damping force. Deflecting force will move the pointer from its 0 position. Controlling force will stop the pointer at its actual value where we have to take the readings, and the damping force, it will remove the oscillations such that we can take the actual reading. Okay, that was all for today. Thank you. Stay connected.